Okay, so what I want to do now is to look at linear transformations coming from matrices in more detail. In particular, we're going to look at square matrices almost exclusively for the next chapter. So let's take A, an n by n matrix. So that means n rows and n columns. So the aim is to, well, I suppose, understand the linear transformation TA from Rn to Rn, so that sends, remember, x to Ax in more depth. It's that simple. So we've got a lot of practice at kind of understanding how various properties of matrices translate to various properties of this. For example, if the columns are linearly independent, then the linear transformation is one-to-one, things like that. But we want to be a bit more detailed now. We want to really understand exactly what about the matrix, what the matrix means for the linear transformation. So let's do a quick example. So let's do the following. So let me give you a matrix, a 2 by 2 matrix, 2, 0, 0, 3. And let's think about this linear transformation. In particular, I'm going to think about what it does to the standard basis. So A of E1, remember what's that equal to? That's just equal to the first column. But if I'm going to write this out longhand, it's 2, 0, 0, 3, 1, 0. So multiplying that out gives me 2, 0. So that's equal to what? Well, it's worth noticing this is just 2 times E1. In other words, when I feed in E1 into the linear transformation given by A, I just scale E1 by 2. Similarly, if I was to do E2, well, the same logic gives me 0, 3. And that's what? That's 3 times E2. So again, E2 is the same kind of interesting property. If I'm feeding it into this linear transformation, all I'm doing is scaling the vector by the constant 3. So why is this useful? Well, first of all, we know that the vectors E1 and E2 form a basis. So if I take A, x, or I have a general x now, so if this x was equal to x1, x2, let's say, then this would be, well, A of linear combination x1, E1, sum x2, E2. Remember, I can write down any element in that form. It's one of the nice things about the standard basis. But now linearity tells me what? This is equal to x1, A E1, plus x2, A E2. And I know what these two are. It's just scaling by either 2 or 3. So this is equal to what? This is equal to, well, 2, I'll move things around, about 2 x1, E1, plus 3 x2, E2. So knowing what happens to E1 and E2, along with the fact they're a basis, tells me everything about this linear transformation. And of course, I could write this down in a more concrete format. This is just 2x1 times 3x2. So neat. So this property of having a vector being fed into the linear transformation and then just being essentially changed by a scalar is a really useful one. And it's one I want to single out. So definition. So let's take A, an n by n matrix. So take an n by n matrix. An eigenvector of the matrix A is a vector, surprise, surprise, I'll say V in Rn, such that what? First of all, it's non-zero. So that's kind of important for technical reasons. I'll explain why in a second. 2, AV is equal to lambda V. So that's the crucial thing. And this is for some lambda in the real numbers, so for some scalar. So this lambda is kind of important. I mean, we call any such lambda an eigenvalue. value of A. So the eigenvalues of A are explicitly the scale terms that turn up when I look at eigenvectors. So this is a very important definition. I mean, it's maybe worth saying here why I want the non-zero condition. If I allowed, so this is going to be as an aside, if I allowed 0, if v is equal to 0, well, this implies this condition holds for every lambda. Which isn't something we want. We want a situation where any eigenvalue or eigenvector has a specific eigenvalue associated to it. You see, if v is not 0, you can't have two different possibles. So this is kind of a subtle point. So we don't want this to happen, right? So we don't want this. Okay. It's not obvious yet why, but I don't want to have the 0, because 0 would be kind of trivial in a sense. Okay, so let's just do a quick example, shouldn't we? So let's do what I've just done. I mean, if A is equal to 2, 0, 0, 3, what do we see? Well, we saw E1 at least is an eigenvector of A with eigenvalue 2. E2 is an eigenvector of A with eigenvalue 3. In fact, you can probably guess what the general case of this type of thing is. But first, before I do that, I need to single out what's special about this matrix A. So definition. Lots of definitions in this lecture. So let's have A, again, an n by n matrix. This is diagonal if and only if the ijth entry is equal to 0 for all I not equal to j. So explicitly what that means is the following. A looks like a square matrix where I have lambda 1, lambda n down the diagonal, and 0 everywhere else. So this diagonal is kind of the main diagonal that we've seen in the identity matrix. It's called the leading diagonal. So something to say here is, if you're diagonal, you're 0 off the leading diagonal. But remember, lambda 1, these guys, I mean, they could be 0. There's nothing stopping this. So the 0 matrix is an example. So is the identity matrix. So examples, the identity matrix. It's 1 down the leading diagonals, or kind of 0, kind of the 0 matrix. Nothing stopping you there. The main thing is you've got to be 0 off the diagonal. Okay, so here's a nice fact for us, which kind of ties more what we've just seen. Again, if I have an n by n matrix, diagonal, if and only if the collection E1 to En are all eigenvectors of A. It's kind of an interesting way to think about a diagonal matrix. Let's kind of think about this really carefully. I mean, A of EI is equal to the ith column of A. It's always the case. It's one of the nice things about the standard basis. So this implies what? Well, if this is equal to lambda I EI, this is for all I. This is if and only if. Well, what are the options? A is equal to the matrix I've just written above. Lambda 1, lambda 2, dot, 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 to lambda n, 0 is everywhere else. So this is a pretty nice fact. I mean, very concretely as well, if you want to kind of go back to kind of the previous, I mean, if I take A of x, so where x is equal to, in fact, let me write this like this. If I do a of x1 dot 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 down to xn, this is equal to what? It's great, you just term by term multiply by these. So that's a really explicit way of thinking about this linear transformation. It's kind of the best possible situation. So you're just scaling each term individually by some choice of numbers. Okay, so the question at this point is the following. So if I'm a diagonal matrix, I can spot a bunch of eigenvectors. That's great. I mean, something to think now is if I give you an eigenvalue, how many eigenvectors are there which have that as eigenvalue? That's an interesting question. How many eigenvectors correspond to a given eigenvalue? It's an interesting question. So what I want to do is sort of gather together all eigenvectors with a specific eigenvalue. So let's choose again, as always, an n by m matrix. And just choose lambda any number. So lambda in R. I'm not making any restrictions on this at all. So definition. The lambda eigenspace, so it should be one word, the lambda eigenspace of A, it's equal to the union of two things. So the first thing is, I can write that a bit more neatly. So it's going to be the collection of eigenvectors of A with eigenvalue lambda. I should maybe say this could be empty. There could be no eigenvectors with eigenvalue lambda. And in addition to this, I want to also include the zero vector. It's kind of a bit strange, but I want to include it in there. So first and foremost, what is all this? Well, A is an n by n matrix. Eigenvectors are vectors in Rn. This is a subset of Rn, first and foremost. So what I need to really do is understand the eigenspace. That's the plan. So the eigenspace essentially is a way to collect all the potential eigenvectors for a given eigenvalue. So let's try it. So let's think about the following. So observation. So we need to really concretely understand this eigenspace. I mean, I've used the word space, so we probably should justify it's a subspace or something like that, shouldn't we? So let's do this. So V is in the lambda eigenspace if and only if, well, AV is equal to lambda V. So this is a pretty great fact because, I mean, this condition is exactly what the condition of the eigenvector is, but we've just seen, I mean, this always holds for 0. So this is great. This is an if and only if condition. So this AV is equal to lambda V exactly captures the eigenvectors with eigenvalue lambda and the 0 vector. So this is if and only if, so I need to try to kind of reinterpret this in a way which I'm familiar with. So let's move everything to one side. Again, it's still not that familiar, but maybe I could try to take out a factor of V using some matrix algebra. So this is if and only if A minus lambda In V is equal to 0. Now, why is this good? This is good because this is exactly the kind of statement that we've seen when we've been thinking about null spaces of matrices. So this is if and only if V is in the null space of A minus lambda In. Okay, so this is kind of a bit crazy, but we're not talking about the null space of A here. We're talking about the null space of A minus lambda In. And we're looking at that because we're trying to re-express this concept in terms of something more familiar. So what does this mean? Well, it's saying you're in the eigenspace if and only if you're in the null space. Well, that means the eigenspace is the same thing as the null space. So, conclusion. The lambda eigenspace of A is literally equal to the null space of this modified matrix A minus lambda in. So what does this tell you? Well, this immediately tells you that the lambda eigenspace is a subspace, because null spaces are kernels of linear transformations. That makes them subspaces. So the lambda eigenspace of A is a subspace. Everything's an n by n matrix, so it's a subspace of Rn. Pretty neat. So, what does it mean to be an eigenvalue? Well, observe that lambda is an eigenvalue of A if and only if, so let's get this careful, if and only if there exists eigenvector with eigenvalue lambda. It's kind of strange. So we need an eigenvector to be called an eigenvalue. This is if and only if what? Well, let's go back to the eigenspace. That's if and only if this thing is not empty. So we want there to be something in there. So that's exactly the same statement as saying the eigenspace is non-zero. It's not just the zero vector. If it was just the zero vector, there are no eigenvectors. Right? So it's kind of empty. Well, not empty, but it doesn't contain anything other than zero. So this is if and only if what? The null space of A minus lambda in is non-zero. So that's a kind of an interesting way to think about eigenvalues. I can convert the idea of lambda being an eigenvalue into a fairly abstract statement about the null space of a specifically chosen matrix. Okay, so what we want to do now is to actually try to work out eigenspaces in a specific example. So let's do kind of a nice, simplish case. Let's do A is equal to 2, 0, 0, 0, 2, 0, 0, 0, 3. So a diagonal matrix. We've already seen how to deal with or find at least eigenvectors for a for a diagonal matrix. So it stands to reason we should check eigenspaces in this case too. So let's think about the 2 eigenspace. The reason I'm thinking about the 2 eigenspaces is because, well, I definitely know 2 is an eigenvalue because E1 and E2 both have 2 as an eigenvalue. So it seems worthwhile to do so. This is equal to the null space of what? Well, it's going to be 2, 0, 0, 0, 2, 0, 0, 0, 3 minus, what is it, 2 times 1, 0, 0, 0, 1, 0, 0, 0, 0. It's me just doing the above. So this is equal to what? The null space of 0, 0, 0, 0, 0, 0, 0, 0, 1. So we need to work out this null space. And how do I work out the null space of a matrix? Well, I just find the general solution to the homogeneous problem. So let's write down 0, 0, 0, 0, 0, 0, 0, 0, 1. This is an incredibly simple example, but I'm going to do it properly just to illustrate how you do it in general. So you'd take this guy and you'd put it in echelon form, or reduced echelon form to be really slick. So I just flip the first and the third row here, so that's what I'm going to do. Okay, so that's in reduced echelon form. It's kind of unnecessary, but what this does imply is what is x3 is equal to 0. So this tells me that the 2 eigenspace of A is equal to, well, remember what it is, it's the null space of this. And now this is going to be equal, I've got 2 free variables. I've got x1 and x2, they're totally free, and x3 is set to 0. So this is just the vectors x1, x2, 0. Remember how we write down a basis for this? We basically split apart the 2 free pieces. So in this case it's particularly simple because this breaks apart as x1, 1, 0, 0, plus x2, 0, 1, 0. So I have a basis. So what is true? This is equal to the span of E1 and E2. So the key takeaway here is the following. I mean, there are several key takeaways, but in this situation, the 2 eigenspace of A, if I want an eigenvector with eigenvalue 2, it has to be in the span of E1 and E2. That's exactly where I have to look. So this is a pretty killer way to work out all eigenvectors with a specific eigenvalue. It's just a null space computation. The crucial thing is getting this matrix correct and then working out the null space using all of our previous techniques. Okay, so I should maybe say more generally how this works. I mean, you could probably guess. You see, if we look at this matrix, it's diagonal, so we know E1 and E2 of eigenvalue or eigenvector are eigenvectors with eigenvalue 2. What we've worked out now is actually all eigenvectors with eigenvalue 2 have to be in the span of E1 and E2. You'd probably guess here as well if I asked for the 3 eigenspace, well, the 3 eigenspace actually is spanned by E3. So that's part of a more general principle. So more general, at least the general situation for diagonal matrices. I mean, if A is the diagonal matrix lambda 1, lambda n, zeros, then this implies the lambda eigenspace. The lambda eigenspace is equal to, so this, we've not proven this, but it's true, this is the span of the EI such that what? Such that lambda I is equal to lambda. That's what the lambda eigenspace is. So just a quick example, e.g., I mean, if I took A as what I had before, actually, I'll do something different. We'll do 1, 2, and 3, 0, 0, 0, 0, 0, 0. And the 1 eigenspace is equal to the span of E1. The 2 eigenspace is equal to the span of E2. You guessed it, the 3 eigenspace is equal to the span of E3. Now you might ask, what happens if I choose lambda where it's not 1, 2, or 3? Well, in that case, you won't get any eigenvectors. So the lambda eigenspace would just be 0. Okay, it would be the 0 vector alone. Okay, so we've not really justified that, but this is kind of the general picture, at least for diagonal matrices. So at this point, if I have an eigenvalue lambda, I know how to work out the eigenspace. It's just the null space of a specifically chosen matrix, A minus lambda In. So that's not too difficult, but we do need to know where my eigenvalues are. So that's a bit of a problem. So the question at this point becomes, how do we determine the eigenvalues of a matrix A? That's the question. You see, if I know what the eigenvalues are, I can find the eigenspaces, if I want to find them, just by doing the null space computations. But what are the eigenvalues? That's the issue. So let's kind of go through this carefully. So we've just seen that lambda is an eigenvalue of A. Well, this is if and only if what? Well, we've seen a moment ago, if we go back up to this, so lambda is an eigenvalue if and only if all this is true. So maybe I'll just copy this because it's worth having it in front of us. Okay. So let's remember A minus lambda In is a square matrix. And the null space is non-zero. Well, that's if and only if the columns are linearly dependent. So there's lots of ways I can proceed here, so many equivalent ones. But the columns of A minus lambda In are linearly dependent. Well, that means there are free columns. That means there's not a pivot in every column. That means you're not invertible. So all these if and only if conditions. So this is if and only if A minus lambda In, not invertible. Remember, it's a square matrix, so this kind of is a meaningful question. And how do I check invertibility? Well, invertibility can be checked with a determinant. This really is the killer application of determinants in this class. We're going to use them to find the eigenvalues of a matrix. So, let's do a little sanity check. If I want to know if lambda is an eigenvalue of A, I need to work out the determinant of the matrix A minus lambda in. If it's 0, lambda is an eigenvalue. If it's non-zero, lambda is not an eigenvalue. So what we need to do is to come up with a clever way to determine the lambda where this happens. So the problem is, lambda is in a sense a variable. Lambda could be any real number, right? I'm moving lambda around. So I need to kind of take into account all possible lambdas. So here's a brilliant way to do it. So bear with me. So I need to come up with a way to exploit this fact. So the characteristic polynomial of A, again, an n by n matrix, is given by the function, the determinant of A minus x in, where we think about x as a variable. Now this is a pretty curious definition. First of all, why does it even make sense? When we think about x as a variable, that means this matrix A minus x in is actually going to look like a matrix whose, at least diagonal entries, are polynomials. So what is the determinant of a matrix with polynomial entries? Well, thankfully, remember, the definition of a determinant is purely algebraic. It just involves adding and multiplying the entries of my matrix. I can add and multiply polynomials, so I can use exactly the same kind of algebraic definition of the determinant, this brutal thing about marching along a row and doing kind of an alternating sum of your determinants of cofactor matrices or something nasty. So this is going to make sense. Let's kind of do an example before I launch into why it's a useful thing to do. So I think it's really important you see this done in practice. So let's take a specific matrix. Let's do A is equal to 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. I'm choosing this because it's a bit more difficult than a diagonal matrix. We'll come back to the diagonal matrix case in a bit, but do this. So what does this imply? Well, what is A minus xi3, because it's a 3 by 3 matrix? Well, it's a 3 by 3 matrix again. It's a kind of a different one than normal, though, because we're going to be taking away x all the way along the leading diagonal. So this is 1 minus x. It would be 3, 3, 3, is that right? Then minus 3, minus 5 minus x, then minus 3, then 3, 3, 1 minus x. Very curious. Okay, so let's work out the determinant here. Where am I? So what is the determinant? Well, I'm just going to use the first row and I'm going to do the general definition of the determinant. I could try doing some sort of row reduction, but it's a bit tricky because in this top corner I involve a variable. And if I'm going to do this kind of row reduction to try to put it in echelon form, I would need to do all sorts of weird scaling. Something you can do, though, if you want to try that, is you could put it into a more appropriate form by switching the first and the third rows. If you do that, the 3 would jump to the top position here, and you can more easily use that to eliminate what happens below. It's still quite an algebraic nightmare, but it is possible. So instead we're going to use the direct definition of the determinant. So the determinant of A minus xi3 here is horrific. So it's going to be 1 minus x times the determinant of minus 5 minus x minus 3, 3, 1 minus x. There's no way I can simplify any of this yet. I've got to go through the full procedure. Minus 3 times the determinant of, oh God, is it minus 3, 3, 1 minus x. Then it's plus 3, remember you've got to alternate, of minus 3, minus 5 minus x, 3, 3. I think that's it. And now remember the determinant of 2 by 2's is AD minus BC. So this absolute nightmare turns into the following. It's 1 minus x. Okay, dear God, here we go. It's going to be minus 5 minus x times 1 minus x minus 3 times 3. That's the first piece. Minus 3. Minus 3 times 1 minus x minus 3 times 3. And then finally it's plus 3. Minus 3 times 3 minus 3, oh God, times minus 5 minus x. Heaven help us. So when you go through all of this and simplify it, gather terms, it's going to take you some time. This will eventually turn out to be minus x to the 3 minus 3x squared plus 4. Whoopie-doo. Okay, so we've got to be kind of intuitive here. What's going on? I'm taking a matrix, A, and this strange procedure, I'm constructing a polynomial. Okay? Now, why have I constructed this polynomial? Well, let's gather a few facts about it first. So, facts. I mean, first of all, if A is an n by n matrix, this implies the characteristic polynomial, first of all, it is a polynomial, requires a bit of work, but it's of degree n. See, in the above case, we had a 3 by 3, and in that case, what happened? In the 3 by 3 case, I got a degree 3, a cubic equation. That's the first thing. Second thing, and this is the most important thing, lambda an eigenvalue of A if and only if lambda is a 0 of the characteristic polynomial. Why is that the case? Well, i.e., if I feed in lambda into my characteristic polynomial, I just get what I was interested in before. And we know that I'm an eigenvalue if and only if that's equal to 0. So this characteristic polynomial is an ingenious way of bundling together all of these determinant calculations into one object. I made the observation that lambda really is a variable, so I do the calculation like it's a variable. That's why I replace it with an x, just to illustrate the fact it's a variable. It all works perfectly well because I can add and multiply polynomials, so the determinant makes sense. The moment I restrict to a specific number, it's just det of a minus lambda in. Brilliant. So what does this mean? This means to find eigenvalues of A, I have to construct a polynomial and find the zeros. So I've traded one kind of very abstract linear algebraic question for one that's pretty concrete in the world of straight up algebra. So properties 1 and 2 give rise to the following. So an eigenvalue is a root or a 0 of the characteristic polynomial. How many of those can there be? Well, various pieces of kind of elegant algebra guarantee the following. You can't have more than n distinct zeros for a degree n polynomial. So that's quite a hard result in abstract algebra, but it's kind of intuitively true, or intuitively believable, sorry. So that means what? Well, A has at most n distinct n distinct eigenvalues. Beautiful result. So when we started off with this, I mean, for all we knew, every single number was an eigenvalue. Right? For all we knew, that was the case. But now we've seen it can't be the case. Right? So it's a really brilliant fact. It's only at most n, and it's because of the algebra, right? That's not at all obvious if you're doing this purely linear algebra. We've had to convert to a polynomial, and then we realize eigenvalues are zeros of polynomials, and in algebra we know that the number of zeros of a degree n polynomial cannot be more than n. intuitively it's kind of believable, isn't it? You can't have 3 distinct zeros for a quadratic equation. It's the same logic works in general. It's quite a difficult piece of algebra to prove it, but at least it's believable. So this is really awesome. It's very similar to when you learned about homogeneous second-order linear equations, so differential equations, sorry, and you thought about solving them. So things like y double prime plus by plus cy is equal to 0. How did you solve that? Well, what you did was you essentially tried to find solutions of the form e to the rx or something like that, and you realized that there was a polynomial flying around in the background. And in 1b at least, it's called the auxiliary polynomial. And you use that auxiliary polynomial to determine important information about the solutions. It's the same thing here. We have an abstract object in mathematics, a n by n matrix. We are associating by this kind of clever procedure a polynomial, and the zeros of it have meaning, back where I started. It's the same kind of abstract idea. So let's just look at this specific example again. It's always like important when you can translate one problem in mathematics to another part of mathematics. It means there's got to be some sort of depth and richness to the problem. So for example, A, exactly as before, we'll do 1, 3, 3, minus 3, minus 5, minus 3, 3, 3, 1. This guy, we've just done the work. The determinant of this, A minus xi3, what was it equal to? It was minus x cubed minus 3x squared plus 4. So we need to find the zeros of this. Well, notice 1 is a 0, because minus 1 minus 3 plus 4 is 0. That means x minus 1 is a factor. So if you do some long division on this, eventually you'll pull out the following factorization. Okay, and for those of you who are terrified, I'm going to be asking you to do long division of polynomials and tests. Don't worry, I'm not. I can barely remember how to do it as well. Anything I give you will be fairly easy algebraically to deal with. So what does this mean? Well, what are the zeros of this polynomial? There's 2 of them. There's 1 and minus 2. So this tells us that the collection 1, minus 2 are the eigenvalues of your matrix A. Isn't that brilliant? So those are the only possible things that can turn up as the scale factors for eigenvectors. So this is a fantastic result, right? It's brilliant. It's a conversion from something in linear algebra to something in just abstract algebra, the idea of zeros of polynomials. So we should maybe also notice that in this case there's kind of a difference between 1 and 2 or minus 2 here, because minus 2 is kind of turning up twice if I look at the characteristic polynomial. So I'll introduce a definition for this. It's not going to be too crucial for us, but it's kind of good terminology to know. So let's have lambda an eigenvalue for A. So that means it's a 0 of the characteristic polynomial. The algebraic multiplicity of lambda, it's kind of a funny expression, is equal to, by definition, the number of times x minus lambda divides the characteristic polynomial. So if lambda is a root, it has to divide it at least once. It's a basic algebra, so the number of times that happens, that's the algebraic multiplicity. So just as an example, if A is equal to, well, the same guy as above. In fact, let me just copy it. So this implies what? Well, the algebraic multiplicity, maybe 1 has algebraic multiplicity. Oh my goodness. So 1 has algebraic multiplicity what? Well, x minus 1 and divides it once. And 2 has algebraic multiplicity, or minus 2, sorry. 2, because x plus 2 divides it twice. Okay? So it's kind of a funny number associated to an eigenvalue. It really only makes sense once I convert to the algebra, once to the characteristic polynomial. It's not obvious what it means purely in the world of linear algebra. Something as well to say here is this is a big warning. If you think about this, there's some very strange consequences. It is possible for A to have no real eigenvalues. Why is that true? Well, remember there are examples of polynomials with no real roots. So just e.g., I'll do one I've deliberately rigged here. Let's do A is equal to 0, minus 1, 1, 0. If you do the characteristic polynomial of this, it turns out to be equal to x squared plus 1. And that's got no roots in the real numbers. Now, it does have roots in the complex numbers, and you can try to make sense of this in the complex world, but you would need to extend the concepts of real vector spaces to complex vector spaces. It's not so difficult. You just replace all of your kind of defining properties with the usual ones where you allow scalar multiplication by complex numbers as opposed to real numbers. It's not the kind of thing we're going to do in this course. There may be a few occasions that I invoke it, but not really in a kind of a general sense. Something to say as well, why is this happening intuitively? Well, this is a 2 by 2 matrix, so it represents the transformation from R2 to R2. If you were to really sit down and think about this, this is counterclockwise rotation by, I think it's pi over 2, so by 90 degrees around 0. So why do I expect there to be no eigenvalues? Well, no eigenvalues means there's no eigenvectors. And if you're rotating, that means you're not scaling any vector by a constant. Remember what happens when you scale? It has to move along the straight line between it and the origin. So if you're rotating everything by pi over 2, nothing in all of R2 gets scaled, apart from 0 itself, but that's not an eigenvector, right, by definition. So because it's a rotation, no non-zero vectors are scaled by a number. So this is totally ingenious, right? This is a really elegant algebraic version. So the fact x squared has no roots, or x squared plus 1 has no roots, is a manifestation of the fact that rotation around the origin by pi over 2 cannot scale any non-zero vectors. Okay, this is all well and good, but let's bring this back to a kind of a more concrete, easy to deal with case. So there's a really important theorem that I want to kind of prove for us now. The eigenvalues of an upper triangular matrix are the entries in the leading diagonal. Okay, so let me prove this. So that includes so remember what upper triangular means. I should remind us what this means. I'm going to prove this because it's a good illustration of the power of this technique. So let's do upper triangular. A matrix is upper triangular if it's A11, A22, dot, 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 down to ANN. Anything can happen above it, but everything below has to be definitely 0. So diagonal matrices are examples of this. So I'm claiming that the diagonal entries, A11, A22, ANN, those are precisely the eigenvalues. So why is this the case? Well, let's go through it. So this implies that A minus xin is equal to what? Well, it's going to look like the following. It's going to be A11 minus x, A22 minus x, dot, dot, dot. Is it ANN minus x, star up here, 0 here. So what does this mean? Well, what's the determinant of an upper triangular matrix? It's the product of the entries down the diagonal. So this implies the determinant of A minus xin, the characteristic polynomial, is the product of these things. A11 minus x, A22 minus x, dot, 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 all the way down to ANN minus x. So what are the zeros of this? Well, it's precisely the diagonal entries. This implies set A11 dot a and n are the zeros of the characteristic polynomial. And that, of course, implies now, by all of our hard work, that these are the eigenvalues of A. Proof. So I want to make a warning at this point. When you do row reduction, so warning, row reduction alters the characteristic polynomial. Or maybe I should say row reduction does not preserve the characteristic polynomial. So that means if you take your matrix and you put it in upper triangular form by doing row operations, that tells you nothing. Right? It'll tell you what the determinant of A is, brilliant, but you don't want that. You want the determinant of A minus X in. So for example, just in general, what I'm saying is the following. If I give you a matrix A, and I do row operations to put it in the form, I don't know, lambda 1 to lambda n star 0, it's very important you understand that this does not imply at all that the determinant of A minus Xin is equal to, well, lambda 1 minus X dot 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 to lambda n minus X. That's a really important misunderstanding. If you write A minus Xin down as a matrix and then do row operations to put it in upper triangular form, then you've got your correct, then it's fine, right? Because it's all baked into it from the beginning. But every time you do a row operation, you're changing the characteristic polynomial, so this is totally no good. Just because the characteristic polynomial of this side is this, doesn't tell you anything about the characteristic polynomial of the other side. So it's a classic mistake. I've seen it many times. You can't do that. So the problem with the characteristic polynomial is it's computationally difficult to work out because you have to work out this determinant directly, right? There's no kind of easy way to do it. But once you have it, it's incredibly powerful, okay? Because you end up with a situation that you can convert all these difficult abstract questions in linear algebra to questions in kind of just zeros of polynomials, which is much more straightforward to deal with. Okay, so I should say this is, I'm not saying this is never true, but if you give a general matrix and then you put it in upper triangular form using row operations, in no way does that preserve the characteristic polynomial or anything like that. Okay, so that's a good place to stop.